Very good morning to everyone. I am Shubhangi Rao, working as an assistant professor in Department of EEE at MLR Institute of Technology. Here I am teaching this subject electromagnetic field to second year EEE students. And today we are going to discuss about coordinate systems and their transformation. So before starting the coordinate system, let us discuss few points about the electromagnetic. So what is electromagnetic? It is a branch of physics, or you can say electrical engineering, which is used to study the electric and magnetic phenomena. The electric and magnetic fields are closely related to each other, and as we know, the field is a function that specifies a quantity everywhere in the region or the space. If the field produced is due to magnetic effect, it is called as magnetic field. Similarly, the field which is produced by an electric charge is called an electric field. Now, the moving charges, if they produce the current, and current carrying conductor produces a magnetic field. In such case, the electric and magnetic fields are related to each other, and this kind of field is called electromagnetic field. If we discuss about the applications of electromagnetic field, there are various applications. Some of them are here in the slide. We have application of EMF in electrical machines. We have the application of EMF in radio frequency communication, microwave engineering, satellite communication, radar technology, antenna technology, nuclear research, fiber optics, electromagnetic interferences, and many more applications are there. Before starting coordinate system, we should know about scalar and vector also. So, as we know, various quantities are involved in the study of electromagnetics, and they can be classified as scalar as well as scalar and vector. So, what is a scalar quantity? A scalar is a quantity which is characterized by its magnitude. Means it has magnitude but it does not have any direction. And the examples are temperature, mass, volume, density, speed, and electric charge, and some more examples are there. If you talk about vector quantity, a vector is a quantity that is characterized by both its magnitude and its direction. Means a quantity which is having magnitude as well as it has direction. The examples are force, electricity, displacement, electric field intensity, magnetic field intensity, acceleration, etc. So this is about scalar and vector quantities. Now let us start coordinate system. So what is coordinate system? See, why there is a need of discussing coordinate system, we should understand that a coordinate system is a system that uses one or more numbers or coordinates to uniquely determine the position of the points or other geometric elements on the space. You can also define it as the physical quantities which we shall be dealing with in electromagnetic field. They are the function of space and time. So to describe the special variation of these quantities, we require an appropriate coordinate system, which may be orthogonal or non-orthogonal. So that is a coordinate system. In simple language, we can say to uniquely determine the position of the points in the space, we need a coordinate system. As I said, we have two types of system, orthogonal coordinate system and non-orthogonal coordinate system. So what is an orthogonal coordinate system? It is a coordinate system where the coordinates are mutually perpendicular to each other. For examples, Cartesian or rectangular coordinate system. Another one is circular cylindrical coordinate system, and we have also spherical coordinate system. We have more orthogonal coordinate system, but these are the three systems which we are going to deal with in electromagnetic field subject. Also, as I said that we are going to discuss about the transformation. So there may be some problems which are easy to solve in one coordinate system, and some other problem may be easy to solve in another coordinate system. So there we have the requirement of transformation, means one coordinate system can be transformed into another coordinate system. So this we will do as per the requirement of the question. Now if we say a non-orthogonal system, actually they are hard to work with and their practical uses are very less. So we are going to discuss about and we are going to use orthogonal coordinate system. So first orthogonal coordinate system, as I said in the previous slide, is rectangular or Cartesian coordinate system. So what is that system? Basically this is the most common and often preferred coordinate system, and it is defined by intersection of three mutually perpendicular planes. Before going through the planes, first I would like to draw this three perpendicular axes where we are going to have these planes. So if you see in this diagram, we have three axes which are perpendicular to each other. Perpendicular means they are having the angular difference of 90 degree. So this is our x-axis, this is our y-axis, and this will be our z-axis. So these axes are perpendicular to each other, and as we are saying in the definition that it is an intersection of three mutually perpendicular planes. So planes can be formed by using these axes. So if you see, this is the first plane. Here you can see there is a plane which is called x constant plane, and you can clearly see this is here in y and z direction. So basically this plane is formed between yz axis and z axis. That is why it is called yz plane. It is also called x constant plane because if you see in this x axis at a particular point, for example this point is x is equals to 2. So at x is equals to 2, this plane is formed, and we are calling x constant because x would be constant, but there may be the variation in y side and z side. So this kind of plane is called x constant plane. Similarly, we have y constant, or you can call it xz plane because this plane is formed between x axis and z axis, and again we are calling it y constant plane because at a particular point this plane is formed in the y axis, but there may be variation in x direction and z direction. So this is called xz plane or y constant plane. Similarly, we can have z constant or xy plane. So here z is constant because at a particular value of z we can have this plane, and here there will be a variation in x and y direction. So this is called z constant plane and y constant and xy plane. So if you combinedly draw it, you can clearly see in this diagram we have three axes and we have three planes. So this is your z constant plane, or this is written as z is equals to 0 plane because it is here at 0, x is equals to 0, y is equals to 0, z is equals to 0. Here if you see z maybe is equals to 2, so that is also called z constant plane. Here z is equals to 0, still it will be called as z constant plane because z would be constant and there would be variation in x and y direction. So this plane is called z constant plane, this one is called x constant plane, and this one is called y constant plane. So here we can clearly see that three planes are mutually perpendicular to each other. And if you talk about, as I am saying, that there would be variation in maybe x direction, y direction or z direction. So, what would be the range? So, the range for x-axis, it would be from minus infinity to infinity. Similarly, for y also, it will be minus infinity to plus infinity, means x-axis can be extended from minus infinity to plus infinity, y can be extended from minus infinity to plus infinity, and also z can be extended from minus infinity to plus infinity, means it can go in this direction also, like this. So, for example, this is z, this is plus infinity, but here it is minus infinity. Here x is plus infinity and this is minus infinity. Similarly for y also. So, this is the basic introduction of rectangular or Cartesian coordinate system. Let us move to next slide. Let us talk about differential length for this particular coordinate system. So, as I say that there is a variation in x direction, y direction and z direction, and we have planes in, we have yz plane, we have xz plane, we have xy plane, like this. So, if we talk about the variation, if we talk about x axis or x direction, here in this direction we can take the variation as dx, means differential length in x direction. For y we can take this length as dy. In z axis we can take some length as dz. So, this is differential length in z direction, this is differential length in y direction, and this is differential length in x direction. Now, if I want to write dl, then I can write vector dl is equals to dx ax plus dy ay plus dz az. That is the equation. Now, if I want to find out the magnitude of this, I can write mod of vector dl is equals to under root of dx square plus dy square plus dz square. So, here I will get some numerical value, right? And because here we have three planes also, means yz plane, xz plane, also xy plane. So, by having this plane and by having these differential lengths, we can even find out differential volume. So, that differential volume will be equals to dx into dy into dz. So, this is differential length, this is magnitude of the length, and this is differential volume. I hope this is clear to everyone. Let's move to next slide. Now, we will talk about differential surface area. We have surface, so obviously there would be surface area, and we know in particular direction we have variation in two different directions. For example, if I take x constant surface, there would be variation in z axis and y direction, right? And if we talk about this particular surface, so this surface is in yz plane, but it is normal to x axis. So, when we want to find out differential vector surface area, for example, for this particular plane, or you can say in x direction, so that will be called as, that can be written as dsx vector, and it will be written as, we know that the variation is in y and z direction, so it can be written as dy dz, and as it is normal to x axis, so the unit vector would be ax. Similarly, in y direction, when I want to write differential vector surface area, and it is normal to y direction, so it can be written as dx dy ay, where there is a variation in x and z. Similarly, it can be written for dsz, differential vector surface area, which is normal to z direction, and it can be written as dx dy unit vector az. So, these are the differential vector surface area. I hope this is clear to everyone. This was our Cartesian coordinate system. Let us now discuss about the second coordinate system, which is known as circular cylindrical coordinate system. It is also a type of orthogonal coordinate system. Here also we are discussing about the axes which are mutually perpendicular to each other. But what we need to form a cylinder, or what we need to study about the circular cylindrical coordinate system. First we need the plane of a constant z which is parallel to xy plane. So we need a plane of constant z, means this one. Constant z means it will be somewhere at z axis and there would be variation in x and y direction. So this we need, this is one of the plane which we need to form a cylinder. Next one, we need a cylinder of radius r with z axis as the axis of cylinder. So what we need here, we need this. We need a constant radius, or we need a radius for a cylinder, and the axis for this should be z axis. So when we have this, suppose this is the radius and the axis is z. So apart from this constant z plane, we need this. And third one, we need a half plane which is perpendicular to xy plane. Xy plane means this plane, and it is forming an angle phi with respect to xz plane, means this plane, or in simple language you can say it is forming an angle with x axis. So this is the half plane which we need, and it is forming an angle which is given by phi from x or with x axis, and this angle is called azimuthal angle. This angle is called azimuthal angle, right? So what we need is, we need a constant z plane, we need a cylinder of radius r where the axis of this cylinder is z axis, and also we need a plane which will be xy plane, and it is forming an angle phi with x axis. So combinedly they will form a circular cylindrical coordinate system. And if we talk about the ranges for the coordinates, so first we should know the coordinates. So what we are saying, we need z, we need r, and also we need phi. So how do we write it? When I want to, for example, I want to write some point, I want to locate some point. So the coordinates would be r, phi and z. In place of this r, which is defining the radius of the cylinder, in place of this r, even rho can be written. So p rho phi z. So basically, by whether we are using r or we are using rho, we are basically talking about the radius of the cylinder, right? So these are the coordinates, rho phi z or r phi z. So the range for rho or r means radius would be, because it is starting from 0, so obviously its range would be from 0 to, it can go to infinity. So its range would be 0 to infinite. Next, if we talk about phi, which is called as azimuthal angle, as I already told, it is starting from x axis. So the base would be, the reference axis would be x axis, and slowly it will move in anti-clockwise direction. It will go up to here. So basically it is starting from 0 and it is completing one circle. So obviously its range would be 0 to 2 pi. And if we talk about the range of z, it can range from minus infinity to plus infinity. So the range of z is minus infinity to plus infinity. This is the basic of circular cylindrical coordinate system. Let's move to next slide. Now if you see, by using these three elements or by using these three components, we have formed a circular cylinder, or we can say circular cylindrical coordinate system. If you see this keenly, here we can see some intersection points. Okay, So this particular point or somewhere here or here, this is the intersection of R constant and Z constant, and it is forming a circle, this one. Here somewhere, when we have this phi constant plane, somewhere here or here, we are getting the intersection of R constant and phi constant, right? And somewhere here, by combining this, we can get a point which can be taken as P, and its coordinates are, we are getting R, phi and Z. Because here we are getting the intersection of R and phi, and here we are getting, because of the height of the cylinder, we are getting the intersection of R and Z. So combinedly, they are giving us the coordinates R, phi, Z, where R is the radius of cylinder, phi is the azimuthal angle, and Z is the height of cylinder. Next, if I want to write the equation for this point P, or if I want to write the vector equation along with unit vectors, so the unit vectors, as I already know, the coordinates are R, phi and Z. So the unit vectors in R direction, it would be AR. In phi direction, see, in phi direction it can be here, it can be here, it can be here also, and the unit vector would be A phi. And if we talk about Z direction, it would be like this, AZ. So these are the unit vectors, and the equation is PR AR plus P phi A phi plus PZ AZ, where PR is the component in R direction, P phi is the component in phi direction, and PZ is the component in Z direction. So this is the vector P. Next, let's talk about differential length in R direction, phi direction and in Z direction. So here we have taken a small portion of this cylinder. If you see, this is a differential volume, right? So for even having the differential volume also, we need differential length. So what are the lengths required for this volume? So in R direction we need dr. So somewhere here on this R, this can be taken as dr. This is the differential length in R direction. If you talk about dz, somewhere in the Z direction, the small element, this can be taken as dz. What else we need? See, we have got dr, we have got dz. If I try to draw it here, so what I need is, I have got, this is my dr, okay, this is my dz. What else I need? I know, see, this is a circle, so it is not exactly straight line, it is forming a curve. So I need this length also. So how would I get this length? Here you can see we are getting R d phi. Basically R is the radius, d phi is the angle. So radius, angle. What else we need here? Here we are getting this arc. So what will be the relation between arc, radius and angle? Because we have to get radius and angle. So basically angle is equals to arc upon radius. So this arc is given by angle into radius, means this arc which we want here is d phi into r. So we are getting r d phi. So now we have got all these three lengths. So these are the differential lengths. Now if I want to write the vector, it will become dl is equals to dr ar plus r d phi a phi, because it is in a phi direction, plus dz az. Right. Now if you want to find out the magnitude of this, it will become dl is equals to under root of dr square plus r d phi square plus dz square. And now because we have three different lengths, we can get dV means differential volume, which will be given by r dr d phi dz. Let's move to next slide. Now let's talk about differential vector surface area. Just like Cartesian coordinate system, here also we can find out differential vector surface area, which will be normal to a particular direction, right? So if I want to find out the differential area in r direction, so obviously the planes would be, this is our r direction, so the planes would be dz and this arc means r d phi. So in this direction, my differential area would be r d phi dz and the unit vector will be ar, because it is normal to r direction. Similarly, if I want to find out the differential area in phi direction, so it will become, we know the variation can happen in r and z, so this will be dr dz, and because it is normal to phi direction, this is the unit vector a phi. So ds phi we can write it as dr dz a phi. Similarly, we can write for z direction also differential vector surface area, which is normal to z direction. So it will become, for the z direction, the planes would be this arc and radius. So differential radius is dr and this arc is r d phi. So it will become r dr d phi az, means differential vector surface area which is normal to z direction. So this is about circular cylindrical coordinate system. Now we can see, as I said, we can discuss the transformation also. We can convert Cartesian coordinate system into cylindrical and cylindrical into Cartesian coordinate system. So if you notice here in this particular diagram, we have marked the coordinates of both coordinate systems, Cartesian as well as cylindrical coordinate system. So x, y and z, right? So any point if I want to define here, it will be given by p is equals to x, y, z, p x coordinate, y coordinate and z coordinate in Cartesian coordinate system. And similarly, if I want to locate a point in circular cylindrical coordinate system, its coordinate would be r, phi and z. So x, this is x direction, this is y and this is z. Now we need, see, z is common in both of them. What is different? X, y and r, phi. So already we have got x and y. This will be our r, radius of the cylinder, and because it forms an angle with x axis, so this is your phi. Now any point can be located in Cartesian as well as cylindrical, means if any point is given in the Cartesian coordinate system, it can be transformed into cylindrical and vice versa. So how do we get that? We know this is x axis, this is y axis, this is r and this is making an angle phi with x axis, right? So if I want to write x in terms of r and phi, what I can write? This will be, if we draw a perpendicular on this x axis, this components becomes r cos phi. If I draw a perpendicular in y axis, it becomes r sin phi. So we are getting x is equals to x r cos phi and y is equals to r sin phi, and z will be common. There is no change in that. So z is equals to z. Similarly, if I have some points given in Cartesian coordinate system and I want that in circular cylindrical coordinate system, so obviously I need r phi because z would be constant. So to get r, see, this is the resultant of, if you see in this diagram, this will be the resultant of x and y. So if I want to find r, I can simply write under root of x square plus y square. And if I want to find out this angle, I can write it as r sin theta by cos phi theta, or you can write it as y by x. So simply by inversing you can get tan inverse y by x and z is equals to again z. So that is how we can transform Cartesian to cylindrical and cylindrical to Cartesian. So this is about circular cylindrical coordinate system. Next we'll discuss about spherical coordinate system. How do we form a sphere, or how do we get this particular system? So what are the surfaces which we are which we need to define the spherical coordinate system. So again we need three elements. First one is we need a sphere of radius r, where the origin of this sphere would be the center of the sphere. So this we need. So this is the origin, and as we say, we need a sphere of r, right? So this is the first element which we need to form a spherical coordinate system. Second one which we need is a right circular cone with its apex at the origin and its axis on z axis as z axis. This one. We need a cone. In simple language I can say its axis would be z axis and its apex is origin, right? So it is starting like this and it is forming a half angle, or a simply you can say an angle theta with z axis, and it rotates about z axis, right? It rotates, that is why it forms a cone, right? And as I say, it starts from z axis, means we can also define its angle. So basically its angle would, see this cone you can have here also. So this angle would change and it can go up to this point, means it can start from 0 and it can go up to 180 degree. So if we talk about the range of this phi angle, it will be from 0 to pi. Next we need is a half plane which is perpendicular to xy plane and containing z axis, right? And it is making an angle phi with the xy plane. Again we are talking about a plane which is yz. This we have seen already in the cylindrical coordinate system. So it is forming an angle with x axis in anti-clockwise direction, right? And the angle is phi. Again this is azimuthal angle and we know it is starting from x and it is going in anti-clockwise direction. So if we talk about its range, as we already know, it is starting from 0 and it is going up to 360. So this is your azimuthal angle, as we have already discussed. This angle which is forming a cone, this angle is called conical angle. It is given by theta. Azimuthal angle is given by phi, right? And this radius r, if we talk about its range, it will start from origin and it can go up to infinity. So its range would be 0 to infinity. So we can clearly see what are the coordinates we have for this spherical coordinate system. Suppose I want to locate a point, so the coordinates would be r, theta, phi. This r, don't confuse it with the cylindrical coordinate system. In that case, r was the radius of cylinder. Here the r is the radius of sphere. So if you just want to differentiate, you can simply take cylindrical coordinate radius as rho and this one you can take as r, or it's your wish, it's vice versa, that one you can take as r or you can take this one as rho, or if you can just take both as r or rho also, that is fine. You should know about that which one is which radius. So once again we see the ranges. The radius of sphere is ranging from 0 to infinity. This angle which is called azimuthal angle, it ranges from 0 to 2 pi or 0 to 360, and this angle which forms a cone with z axis, it ranges from 0 to 180 or you can say 0 to pi. So this is the introduction of spherical coordinate system, and let's move to next slide. So here you can see by using those three elements, means sphere, a cone, and by using this phi constant surface or this yz plane, we have formed a spherical coordinate system. Here also we have some intersection. Here we have intersection of two surfaces, horizontal circle, this one, right? So this is our sphere of r constant. This cone is of theta constant, and this plane is called phi constant, right? Next, let us discuss about locating a point. Okay, so that is how we have drawn it. Once again, I'll draw it here so you would understand how exactly we draw it. This is your x-axis, this is y-axis, and this is z-axis. So that is how we can form this, right? And this is origin. Yes, this which you can see, this diagram, right? Now if I want to locate a point, first let us draw the angles also. This radius we can have somewhere here, or I'll draw in this direction in diagram. This is your azimuthal angle. Somewhere here you can draw the radius of this sphere. This can be the radius which we have taken as the radius of cylinder. And you can draw this point here like this, right? So here by intersection of these 2 points we can form a point P somewhere here. Let us suppose here I can draw this point here, and if we talk about the coordinates, it would be r theta phi, right? Here also I can write r theta phi, where r is the radius of sphere, right? And if you see here, we can see the unit vectors also. So the unit vector in the direction of r is ar. The unit vector in the direction of phi, it can be here, it can be here, here it is here, a phi, tangential, right? And for phi it is here, a, this is for phi, this is for theta, right? So the same thing we have drawn here, just like this diagram, right? This is the point r, phi, z, these are the unit vectors, and this is the coordinates. And now the vector p can be written as p r a r plus p theta a theta plus p phi vector a phi. Next, we can discuss about the differential lengths. Here also we need to take a differential element which you can see here in the sphere, right? So again you can see there is a small element which we had taken here. Here again, if we want to discuss about the differential lengths and surfaces and also volumes, we should know the differential lengths. So in r direction it is simple, it would be dr only, differential length in r direction. Differential length in this theta direction means in this direction, right? So the surface would be this, right? So again, just like the previous case, here we can take that we need r and d phi, right? So this will be r and d theta. So the differential length in theta direction is r d theta. Differential length in phi direction would be, similarly we can find out this one also, r sin theta d phi. So these are the three differential lengths we have, right? And if we want to write vector dl, it will become dr ar plus r d theta a theta plus r sin theta d phi a phi. If you want to find out the magnitude, you can write it like this: mod of dl is equals to under root of dr square plus r d theta square plus r sin theta d phi square. And as we have differential lengths, we can write differential volume also. When you multiply all of this dr, r d theta and r sin theta d phi, when you multiply all of them, it becomes r square dr sin theta d phi. This is your differential volume. Next, differential vector surface areas. Again, because we have surfaces, So we can find out differential vector surface areas also. And similarly, like previous two coordinate systems, Cartesian and cylindrical, here also it will be normal to one particular direction, right? So if I want to write DSR, means this one. So the surfaces would be this r d theta and this r sin theta d phi. So the surface area becomes, differential surface area becomes r square sin theta d phi, and it will be normal to r direction. If we want to find out ds theta, means differential vector surface area in phi direction, it will be normal to phi theta direction, sorry, not phi, theta direction, right? So this becomes this. We need dr for this and we need r sin theta d phi for this. So it becomes r sin theta dr d phi. Now next one can be written as ds phi, differential vector surface area which is normal to phi direction. So we need this dr and this curve r d theta. So it becomes r dr d theta. So these are differential vector surface areas. Next, we can discuss about relation between Cartesian and spherical coordinate system. Same as we discussed about the relation between Cartesian and cylindrical coordinate system, this can also be done. So in the same system, we have to draw all the points of both the systems. So here you can clearly see we have this three perpendicular to each other axis, x, y and z, right, means Cartesian coordinate system. For a spherical coordinate system, we need r, theta and phi. So just like the previous case, there in previous case we have z common, but here we don't have any point common. So we need to find out all the points, right? So let us locate some point. For example, here I have got xy point with the height. I have got z axis also. So here I can locate my point in Cartesian coordinate system px, y, z. At the same place I can define my points in spherical coordinate system, which is r, theta, phi. But how do we find out? So again, here we have this r. If we draw a perpendicular here, this becomes r sin theta, right? So now this is r and this is r sin theta. In previous case this was r, right? So now if I want to find out this particular element, I have some points in spherical coordinate system and I want to convert that into Cartesian coordinate system. So I want x would be is equals to, if we see here already we have this r sin theta and this angle is phi. So x we will get r sin theta, and because this phi is the angle with x axis, so it becomes cos phi. So this is our x. Similarly we can get y also. So this y will become r sin theta will be as it is, and this will be sin phi, right? And z, because this is r and this is making theta angle with z axis, so obviously this component will be cosine component. So z becomes r cos theta. This. So that is how we have converted spherical coordinates into rectangular coordinates or Cartesian coordinates. Similarly, we can convert Cartesian coordinates into spherical coordinates. So simply the r would be the resultant of all x, y and z. So it becomes r is equals to x square under root of x square plus y square plus z square. If you want to find out angle theta, it becomes cos inverse z upon under root of x square plus y square plus z square. And same as this phi angle, this phi is same. In case of Cartesian and cylindrical, we had z common, but here phi angle, it can be formed as it is. Here we don't have any similarity, but yes, this angle is same. right? So it can be find out as phi is equals to tan inverse y by z. So these were the three different coordinate systems, which is known as spherical coordinate system, cylindrical coordinate system, and Cartesian coordinate system. Cartesian coordinate system is also called rectangular coordinate system. So I hope these three coordinate systems and their transformations are clear to everyone. For any query, you can contact us. That is all for today. Thank you very much.